Hello, and welcome to your Statistical Inference 6 lecture. Today, we're going to finish up talking about frequentist hypothesis testing and set ourselves up to be able to talk about Bayesian hypothesis testing in class. In class, we finished up talking about basically two frameworks for doing frequentist hypothesis testing, the Fisherian framework and the Neyman-Pearson framework. Specifically, we left off with the Neyman-Pearson framework, which basically pits two hypotheses, the null and the alternative, against each other, and uses hypothesis testing as a way to make a decision about whether to reject the null hypothesis or not. One of the things we briefly touched upon in that lecture is the difference between a directional null and a non-directional null. Remember, a null hypothesis is basically trying to define what it means for there to be no effect. And we might have a directional hypothesis where we think a null effect is anything equal to 0 or greater than 0. Or we can have a non-directional null, which doesn't specify a direction for the effect, whether it's positive or negative. It just says the null is that there is no effect, and the alternative is that there is an effect. Directional nulls are really helpful when before we've collected any data, we already know that we have an idea of what the direction of the effect is, and we have absolutely no interest in effects in the other direction. For instance, maybe we think that exercising will improve your lung capacity, and we're not really interested in effects that would suggest that exercising makes your lung capacity worse because physiologically there's no mechanism we can think of that might cause that type of effect. Or maybe we just don't care about effects in that direction. We only want to provide evidence for, if we can, effects that show that exercise is in the positive direction. But other times we have no idea what direction the effect is going to be. And so we can't define a directional null, and we have to use a non-directional null. I would also suggest that using a non-directional null is the right choice if you would be interested in effects on either side. If you would be interested in a positive effect or a negative effect, then you should use a non-directional null. This is because when you use a directional null, we put all of our alpha, our type 1 error rate, in one tail, the tail that we're really interested in using. Whereas in a non-directional null, we take our alpha, the regions that we're going to use to reject the null hypothesis, and we split it between the two tails so that we're able to reject in the positive direction when we get something extreme in the positive direction, and we're able to reject in the negative direction if we get an extreme result in the negative direction. If you can genuinely say to yourself that you would not care if the results were in one direction over the other, then that might be a time to use a directional null. But if you're not sure, or if you would be interested in effects to either side, even if one of them seems more likely than the other, then I would suggest using a non-directional null. Now, all of that to re-emphasize the fact that when we're using a non-directional null, we have what's called a two-sided test. We will reject for extreme values that are at the higher end of our sampling distribution, and we will reject values that are on the very extreme low end of our sampling distribution. Technically, we don't actually have to split our alpha or type 1 error rate evenly between the tails. It's totally valid to put more of it in one side than the other, but traditionally we'll equally split that. So say our type 1 error rate is 5%, then we would put 2.5% on the upper end. So this region contains 2.5% of the density of the sampling distribution. And then in the other tail, we would also put 2.5%. So that's what this is here, is 2.5% of the density in the sampling distribution as well. Together, this means that 5% of the density of our null sampling distribution is going to be in the rejection region, meaning even if the null is true, 5% of the time in the long run, we would expect to falsely reject the null, even though it's true. All right, well, why am I talking about all of this? I want to give you some sort of connection between the frequentist parameter estimation stuff we talked about and the frequentist hypothesis testing stuff we're talking about now. So in the previous lectures, when we looked at all of these like power plots or rejection region plots, we typically looked at ones that had one-sided or directional nulls because visually it's just a little bit easier to understand. But I want to show you what this plot looks like with a two-sided, so a non-directional null. Let's say we take a group of of people and we tell them that they have to sit in a room and listen to people say really negative things about themselves for 10 minutes every single day, and then we're going to measure their depression scores after. In this case, we'll say that our null hypothesis is that doing that has zero effect. So people who have to go through that procedure are going to have the same zero average depression scores as the general population. We would be interested in knowing if sitting in a room with people saying bad things about themselves would increase your depression scores, or maybe it'll decrease your depression scores because you hear other people saying bad things, so you feel better about yourself. Because of this, we're going to use a two-sided or directional null. So we want to be able to reject the null in cases where your depression score gets higher, and we want to be able to reject the null in the case that your depression score gets lower. So let's say that we collect this data and we figure out that the sample mean in the group of people that had to listen to people say bad things about themselves for 10 minutes a day is 0.5. So their depression score is a little higher than the population average. We already know how to conduct a Neyman-Pearson style hypothesis test on that and decide whether or not we are going to reject the null. In this case, we can see that we will because the estimate of 0.05 is indeed higher than our rejection region. So why am I going on and on about this example? Well, I want to basically tell you how we could use confidence intervals, that thing that we spent a ton of time talking about last week, to basically perform the Neyman-Pearson style hypothesis test. Notice that in this case, the sample mean that we observed is 0.5. And as you can see from this picture, that is far above the rejection region, which is shown by this dotted line here. So we would reject the null that our treatment group has a mean depression score of 0. In fact, what we observed is that it increases their depression scores. Now, again, on this chart, how we did that was we basically saw that the effect of 0.5 that we observed is far past the rejection region right here, and so we rejected the null. So how do confidence intervals play a role here? Well, here I have multiple versions of that chart, and the only difference is where the actual average effect is. Here you can see that for the alternative distribution, we have an effect around 0.5. Here we have an effect around 0.3, and here we have an effect around, 0.2. Now, what I've added to the charts is the 95% confidence interval. And I want you to pay attention to the fact that 95% confidence interval is going to correspond to an alpha of 0.05. So when we have a 5% type 1 error rate, that is basically corresponding to a 95% confidence interval. Now, what I want you to pay attention to for each of these confidence intervals is whether they overlap with our null effect of 0. Here at the top, we see exactly the same thing we saw on the last slide, which is that we observed a sample mean of 0.5 in terms of their depression scores. And when we calculate the 95% confidence interval, you can see that it does not overlap with 0. And remember, in our actual test, we did reject the null. So our confidence interval doesn't overlap with 0, and we rejected the null. Here we see an effect of about 0.3. And when we look at it, we can see that just barely, this confidence interval does not overlap with 0. It is very, very close to it, but it doesn't overlap with 0. And so we would also reject the null here. In the last example, when we see a population of effect of about 0.2, we can see that the 95% confidence interval does overlap with 0. Now, remember, we talked about a confidence interval representing reasonable values for our parameter estimate. And if 0 is a reasonable estimate for the average depression score in our group, then we can't really reject the null that the effect is 0, because 0 is a reasonable value. And that's true. This is basically the same thing. We can perform this Neyman-Pearson hypothesis style testing by just looking at the confidence interval at the 1 minus alpha confidence level. So if our alpha is 0.5, 95% confidence, and we can just see, does it overlap with the null value? If it does, we can't reject that null value. And if it doesn't, then we can. So now you know a little bit about the connection between confidence intervals and these Neyman-Pearson style hypothesis tests. If our confidence interval contains the null value, then we are not going to reject the null. And if our confidence interval does not overlap with that null value, we will reject the null. All right, so now that we've finished up talking about both Fisherian and Neyman-Pearson hypothesis testing, let's do a quick comparison of them as we close out. So the first thing that I want to talk about is the role of p-values or critical values. In Fisherian hypothesis testing, p-values are used as a continuous measure indicating the strength of evidence we have against the null hypothesis. The smaller your p-value, the stronger your evidence is against the null. However, in Neyman-Pearson hypothesis test, we're really making a binary decision. So our critical values, or p-values as we'll talk about later, basically are a tool that allows you to make a binary reject the null or don't reject the null decision by comparing the results from your data to a given threshold. Fisher and Neyman-Pearson also differ in how they think about error rates. In Fisher's version of hypothesis testing, we're not explicitly making a binary decision, right? The p-values are continuous measures of evidence against the null. So we don't really focus on error rates as we're not really making a binary decision. In Neyman-Pearson hypothesis testing, all we're doing is making a binary decision to reject or fail to reject the null. And so the benefit of the Frequentist framework here is that it controls the type 1 false positive and the type 2 false negative errors by controlling your alpha level. Lastly, these two frameworks differ in their philosophy. Fisher is basically doing inductive inference. He's aiming to measure evidence without making a definitive binary decision, whereas in Neyman-Pearson, we are focused on making a binary decision, and we want to have a procedure that allows us to make these binary decisions in a way that allows us to control the long-run error rates. Now, unfortunately, modern frequentist hypothesis testing has become kind of a weird Frankenstein approach of the Fisher and the Neyman-Pearson hypothesis testing frameworks. They've basically been mishmashed together to the point where we can't really tell them apart anymore. So in modern null hypothesis significance testing, which is probably what you've learned if you've taken any statistics so far, we basically do a Neyman-Pearson style binary decision making, but we do so using p-values rather than critical values. In null hypothesis significance testing, we claim that the null hypothesis is true and try to provide evidence against it using reductio ad absurdum that we talked about earlier. The way that we do this is by calculating a p-value, just like we did in the Fisherian hypothesis testing world, but then we use that p-value not as a continuous evidence against the null, but as a decision-making tool to decide whether the null should be rejected or not. Essentially, we're making the claim that if the null were true, the data that we observed would be kind of absurd, right? It has a very low probability of occurring under the null, and therefore we are going to act as if the null is false, right? Reductio ad absurdum. We assume the null is true, we show that something improbable happens, so we reject the null. And this bears a lot of similarity to both of the frameworks we discussed before, especially because essentially what we're doing is swapping out critical values and test statistics for p-values as a way to make our decision. Basically, instead of checking our test statistic and seeing if it's above our critical value or not, and using that to reject or not reject, we are calculating a p-value and using it and our p-value threshold of alpha to reject or fail to reject the null. Now, you might be thinking, what is the big deal with that? That sounds totally fine to me. We're just swapping out critical values and p-values, and you're pretty much correct. But the problem is that we're mixing up the concepts from Fisherian and Neyman-Pearson hypothesis testing. People basically use p-values to make a decision, but they also at the same time interpret the p-values as a continuous measure of evidence. And those two things are really not compatible. If what you're interested in is a decision-making rule that allows you to control your long-run error rate, then really you just need to know if you've rejected or failed to reject your null. But when people see the p-value, they go, oh my gosh, my p-value is so little, that must be like hugely significant. And that's a bit of a problem because what we're interested in is not the continuous measure of evidence, but the binary decision to reject or not reject the null. This leads to a lot of misconceptions about p-values that we'll talk about in a little bit. So to review, modern null hypothesis significance testing basically mixes the Fisherian and the Neyman-Pearson frameworks, where p-values are used to make binary decisions, but they are also at the same time kind of treated as continuous measures of evidence. This leads to a lot of misuse and misconceptions, like I talked about before. So let's talk a little bit about those misconceptions. Now, as a review, a p-value is the probability of observing a test statistic as or more extreme than the one that we did in our data if the null hypothesis were true. So we are assuming the null is true, and we're trying to see how compatible the data we observed is with that null hypothesis. Now, here are some things that tons and tons of people think are true about p-values, but are not. First, and most commonly, p-values are not the probability that the null is true. And hopefully this makes sense to you with the probability we just defined. If we are assuming the null is true, then the p-value itself could not possibly be the probability that the null is true because we just said we assume it is true. That's like saying, given that the grass is green, what is the probability that the grass is green? Well, 100%. P-values are also not the probability that our effect will replicate. What that means is essentially p-values don't tell you how likely it is that you would get a significant effect if you ran this experiment again. And lastly, and maybe most importantly, non-significant or large p-values do not mean that the null is true. To be fair, under Fisherian hypothesis testing, we are using p-values as continuous measures of evidence against the null, but just because we failed to find evidence that the null is false doesn't mean that it's true. This would be like saying, I didn't find evidence that John Doe is a murderer, so he's not a murderer. It doesn't mean that that evidence isn't out there. It just means that I did not find it. Now, one of the reasons why people have so many misconceptions about p-values is because they're not really taught very well, and another reason might be that they're a little bit counterintuitive to the way that we think. But p-values have become a very integral part of research. It's pretty much it's almost guaranteed that if you're reading some type of empirical research paper, you'll probably encounter a p-value. And of course, things are most interesting when we do reject the null. Usually what we're interested in is that there is an effect. And so often people try and get p-values that allow them to reject the null. Now, if they do that in a way that is statistically inappropriate, this is called p-hacking. And p-hacking is actually a pretty big problem in research. P-hacking basically refers to making decisions about your data, your statistical analysis, specifically to get a p-value that allows you to reject the null. Typically, people use the 5% error rate or an alpha of 0.05 as their threshold. So people are often making decisions trying to get their p-values below 0.05 so that they can reject the null and find an effect. P-hacking is a pretty big problem that would require almost its own class to discuss thoroughly, but what I want you to think about is the fact that if you're going to do frequentist analysis, make sure that you don't make your decisions based on whether or not p-values are significant. For instance, one way that this often comes up is people will add or remove covariates from a regression analysis until the effect they're interested in is significant. Now, first of all, we know from a causal perspective, this is a nightmare. They probably aren't using a DAG to include or exclude things. So they may be impacting the causal estimates that they can make. But specifically, what we don't want is to make decisions based on what makes our p-values low, because that makes our p-values invalid. Another really important concept when it comes to frequentist hypothesis testing is family-wise error rates. One of the huge benefits of frequentist hypothesis testing is that we get to directly choose what our long-run type 1 error rate is, right? It's just alpha, whatever alpha we choose. But where this becomes a little bit of a problem is when we're running a family of related tests all at the same time. Let's say I'm interested in whether the number of jelly beans you consume is related to the number of acne breakouts that you get. And I separately run 20 tests, one for each of the 20 most common jelly bean colors, and see if consumption of that jelly bean color is associated with an increase in acne. I want you to pause and see if you can figure out how to do this calculation on your own. But if I ran those 20 tests and the null hypothesis is true, jelly beans are not associated with acne at all, I want you to calculate the probability that I get at least one significant p-value from the 20 tests that I ran. All right, trusting that you paused and did that calculation, it's 64%. For this family of tests, 64% of the time, I will get at least one significant p-value, even though my nominal type 1 error rate is 5%. The way we can calculate that is by doing 1 minus the probability that we get all 20 non-significant p-values. This is going to be 1 minus alpha, or 0.95 to the 20th power, and 1 minus that to calculate the probability that we get at least one significant p-value. Now, this is a problem. When we're running this many related tests, right, about all of the different colors of our jelly beans, we have now inflated our error rate above that 5% that we expect. When we look at this family of tests as a whole, we now have a 64% chance, more often than not, that we're going to get at least one significant p-value, even though we know that the null is true. I stole this example from an XKCD webcomic that basically talks about the same thing. Here, scientists just keep testing different colors of jelly beans until they find one that has a significant association with acne. In situations like these, our type 1 error rate can be a little bit misleading because while for each test we have a 5% type 1 error rate, when we look at the test as a whole, because if any of them are significant, we are going to claim that there is an effect of jelly beans on acne, then our type 1 error rate balloons to 64%. To correct for the family-wise error rate problem, we often use something like a Bonferroni or a Sidak correction, which basically makes the p-value threshold we're using a lot more stringent so that we're rejecting the null less often, so that in our family of, say, 20 tests, our probability of getting at least one significant p-value is the nominal type 1 error rate of about 5%. Bonferroni and Sidak corrections go about this a little bit differently, but they both have the same goal, making our p-value threshold a bit more extreme. In a Bonferroni correction, we take our alpha level and we divide it by m, the number of tests that we're doing in this family of significance tests. And in the Sidak correction, we use a slightly more complicated but less conservative calculation of 1 minus alpha to the 1 over m power, where m is the number of tests that we're running. What I'd love for you to do as an exercise to the listener is figure out what the actual family-wise error rate would be for these new p-value thresholds. For instance, if we plug in alpha over m as our type 1 error rate for an individual test, what is the family-wise error rate for 20 tests? Same thing with the Sidak correction. All right, the last thing I'm going to talk about when it comes to frequentist hypothesis testing is equivalence testing. Equivalence testing is a little bit different than traditional null hypothesis significance testing, and it provides us a really great tool, which is a tool that allows us to provide evidence for the null. Now, before, when we were talking about null hypothesis significance testing, we made the claim that non-significant p-values do not mean that the null is true. If we find significant p-values, we feel comfortable rejecting the null, but non-significant p-values don't allow us to accept the null. Remember I said it's just the same as saying, well, I didn't find evidence that John Doe is a murderer, so he's not a murderer. Just because I didn't find evidence, right? Just because our test didn't find evidence, it doesn't mean that he's not a murderer. In fact, here's another analogy. I'm going to make a claim that there are no black swans. It's pretty easy to prove this claim is false and very difficult to prove that this claim is true. For example, let's say I go out and I take a bunch of pictures of swans and I find a black swan. Immediately, I know that this claim is false. I saw a black swan, so the claim that there are no black swans is just not true. But it's incredibly difficult to prove that there are no black swans. I would have to look at every single swan in the entire world until I could very conclusively prove that there are no black swans. And null hypothesis significance testing is basically the same idea. If we have a significant p-value, that's like finding a black swan. We can claim that the null is not true. We can reject the null. But proving that the null is true is a lot harder. But equivalence testing, if we're willing to make some assumptions, allows us to do just that. The type of equivalence testing I'm going to talk about is called TOST, or two one-sided t-tests. TOST allows us to provide evidence that the null is true, but we do have to provide it with one thing, an interval null. An interval null is basically a range of values around our null that we think are essentially or practically equivalent to the null, just like the region of practical equivalence we talked about in Bayesian estimation. For instance, let's say I'm trying to estimate the difference in the means of two groups. No effect would be 0. There's no difference between the two groups. But I've basically decided that anything between a -1 and a +1 difference between the groups is practically equivalent to no difference. For instance, let's say I was looking at the IQ of two different groups. We know how much IQ typically varies, so a 1-point difference in the means of the two groups is really not a big deal. So now that we've defined our interval null, anything between -1 and +1 is practically equivalent to no effect. We can use equivalence testing to provide evidence that that null is true. The way we do that, as the name of TOST implies, is by doing two one-sided t-tests. Let's focus on the left-hand blue distribution. This is going to be the first t-test that we do. Remember, a one-sided test basically only rejects values that are extreme in one direction. So here, we're essentially testing against the null that our effect is the lower bound of our interval null, -1. You can see that value with the dotted line here, and our rejection region is highlighted or shaded in blue here. If we look at this test alone, we can see that if we do end up rejecting the null here, we're basically providing evidence that the value is greater than -1. So let's say that that test is significant. We've provided evidence against the null that our difference between groups is -1. Now let's look at our second one-sided t-test. Here on the right in the red distribution, we're testing a different null. The null we're testing is that the difference between the groups is +1, the upper bound of our interval null. Here, we are again doing a one-sided t-test, but this time we only want to reject values that are significantly lower than 1. If we run this test and we reject our null, then we're providing evidence that our value is less than 1. In this case, our null is that the mean difference between groups is 1, and if we reject that null, we are providing evidence that it is less than 1. Now, let's think about this for a second. If we reject the first test represented by the blue distribution, we have provided evidence for the alternative hypothesis, which says that our value is greater than -1. And if we reject the null of our second test, then we've provided evidence for our alternative hypothesis that the value is less than 1. Taken together, we have evidence that our value is greater than -1 and less than +1. And what does that mean? That our effect is likely in that region of values we've determined are practically equivalent to our null value of 0. So by using two one-sided t-tests, we've basically concluded that we have provided evidence that our actual value, the difference in means between these two groups, is in that region that we've determined is practically equivalent to 0. Now, one thing that's difficult about this type of test is we do have to define what that region of practical equivalence is, and that's not always easy. But if we have a way of doing that, either based on our domain expertise or based on some standardized measure, like 1/10 of a standard deviation above or below 0 is practically equivalent to 0, then we have this really powerful tool at our hands. We can actually provide evidence for the null. I want to talk a little bit about the results of an equivalence test using this figure from Daniel Locken's paper that talks a little bit about this two one-sided t-test procedure. Typically, when we run an equivalence test like this, we will also run a null hypothesis significance test testing against the effect of 0. So our null hypothesis significance test tells us whether or not we have evidence that the effect is significantly different than 0, and the equivalence test provides evidence that the effect is practically equivalent to 0. It's within that region, our interval null that we've defined. When we do these two types of tests together, we basically have 4 combinations of things that can happen. Basically, it's every combination of significant equivalence test, non-significant equivalence test, and significant null hypothesis test, non-significant null hypothesis test. This figure shows really well what's going on when these combinations of things happen. Remember I mentioned earlier that we can actually use confidence intervals as a proxy for things like significance tests. Remember, confidence intervals provide a range of values that are compatible with the data that we've observed. In this top row with A, we have an estimate that is statistically equivalent to 0, which means we think it falls within our upper and lower bounds of the interval null we defined, and it's not significantly different from 0, meaning that the confidence interval includes 0, meaning that it is not statistically significantly different from 0. In this case, we have pretty strong evidence that the null is true. Another really common scenario is C, where we have statistical evidence that the effect is different than 0, but the effect is so small that our equivalence test is also significant. We have provided evidence that the effect is practically equivalent to 0. This is really useful because with null hypothesis significance testing alone, we can only provide evidence for the alternative or not provide evidence for the alternative. When we combine it with equivalence testing, we can actually also provide evidence for the null. This is really useful, for example, if you get a non-significant p-value, because it can tell you, is that non-significant p-value non-significant because the effect is very uncertain and we weren't able to exclude 0 from our confidence interval? Or is it non-significant because we're very certain about the effect and we're very certain that it's near 0? In R, there's a package called Toster that will allow you to run these two one-sided t-tests. For instance, here, I'm testing whether the mean anxiety rating of a group that I've sampled is equivalent to the population mean rating of 0. All I have to do is provide the mean, the standard deviation, and the number of values, and then I have to provide my lower and upper bound for my interval null. This will then run my two one-sided t-test procedure and tell me whether the null hypothesis significance test and the equivalence test are significant. Here, the equivalence test was significant and the null hypothesis significance test was non-significant, so I have pretty strong evidence that the mean anxiety rating here is practically equivalent to 0. We can also use this test to make a really cool plot. I really like the one on the bottom, which essentially shows the confidence interval below as well as the upper and lower bounds of our two one-sided t-tests. You can see that our confidence interval is well within those ranges, which is why our equivalence test was significant. All right, to review, we talked a little bit about frequentist hypothesis testing and compared the Fisher and Neyman-Pearson frameworks for hypothesis testing. We also unfortunately talked about the fact that modern-day null hypothesis significance testing is a weird Frankenstein approach of these two frameworks that sort of gets the two of them confused. Lastly, we talked about some pitfalls that come with frequentist hypothesis testing, like p-hacking and family-wise error rates, and some tools that can allow us to use frequentist hypothesis testing in a way that's much more useful for some questions, like equivalence testing. In our next class, we'll talk a little bit about how all of this compares to Bayesian hypothesis testing. All right, that's all I have for you. I will see you next time.